Hello, and welcome to our lecture on sequences and series. This topic does not play a major role in first semester calculus, but it is crucial for second semester calculus, and in particular for one of the advanced placement examinations, the so-called BC Advanced Placement Examination. So it is an important topic, but it often is not part of, again, first semester calculus. We're going to talk about two themes today. One is infinite sequences, and the next one is our so-called infinite series. And the sequence topic will lead very naturally to the topic on series. Let me give you a quick example of a sequence. Suppose you have this string of numbers, this infinite string of numbers, 1, 1/2, 1/3, 1/4, 1/5, etc. I think you see the rule, don't you? Here are some questions. Is that sequence approaching a limit? And by that we mean, is it getting closer and closer to a single number? Well, I think you see the answer, don't you? It's getting closer and closer to 0. Doesn't quite get there, but it gets as close as you want to 0, doesn't it? So those are some of the issues we'll talk about. Let's begin by analyzing some sequences. For instance, let's suppose the sequence is given by the following rule. The nth term of the sequence is 3n minus 2. Now here's what I mean by that. For every value of n, you plug it into the formula 3n minus 2, and it generates a term of the sequence. Here n's an integer. We'll start, say, with 1, n starting at 1, and n goes 1, 2, 3, 4, 5 out to infinity, and it generates the sequence. So when n is 1, it's 3 times 1 minus 2, or 1. When n is 2, it's 3 times 2 minus 2, or 4. When n is 3, it's 3 times 3 minus 2, or 7. I think you see the pattern, don't you? 1, 4, 7, skip 3, 10, skip 3 more, 13. There's a nice sequence. Okay. Here's sort of the technical definition of a sequence. Again, it's one of these definitions where it may be overly complicated, and I think one can understand a sequence without understanding fully the definition. But here's how it goes. It's a function. A sequence is a function, but the domain now is the set of positive integers. And then the function values, the elements in the range, are denoted a sub 1, a sub 2, a sub 3, a sub n, and out to infinity. Those are called the terms of the sequence. Let me show you another example. Suppose our rule for this sequence is 3 plus the quantity minus 1 to the nth power. 3 plus minus 1 to the nth. Here we go. Well, plug in 1 and you get 3 plus minus 1 to the first power. That's just minus 1. 3 minus 1 is 2. Now plug in n equals 2. Well, minus 1 squared is positive 1, so 3 plus 1 is 4. The third term is back to 3 minus 1 because minus 1 cubed is minus. So it goes 2, 4, 2, 4. I think you see the pattern, don't you? It goes like that forever, back and forth between 2 and 4. Let me show you another example. Let's let the nth term of our sequence be 1/2 to the nth power. And I'm going to start this sequence when n is 0. It turns out you can start a sequence with any integer value, n equals 1 or n equals 0, and sometimes they start at 2, etc. That's not the real important issue with a sequence. So let's start it at 0 and plug in some numbers. When n is 0, it's 1/2 to the 0 power, and any number to the 0th power is 1. And then it's 1/2 to the first power, and so a sub 1 is 1/2. And then it's 1/2 squared, which is 1/4. And again, I see a pattern, don't you? It goes 1, 1/2, 1/4, 1/8, 1/16, etc. Now this sequence has an interesting property that the other two sequences didn't have. As we go further and further out in this sequence, it's getting closer and closer to a fixed limit, a fixed number. Can you see what that number is? Yeah, 0. the terms are getting closer and closer to zero. This is similar to the idea of asymptotes that we dealt with much earlier in this course. Remember how we had, say, a vertical asymptote for the function 1 over x. Well, the graph never touched its vertical asymptote, but it got closer and closer to it. So what we say with sequences is kind of the same idea. What we say is this sequence, 1, 1/2, 1/4, 1/8, etc., gets closer and closer to zero as you go further out in the sequence. In fact, you can get as close to zero as you like by going suitably far out in the sequence. So what do we say? We say that that sequence has a limit, okay? It has a limit. It converges. And if you look at the other two examples I talked about, they don't have limits. One of them went 2, 4, 2, 4, 2, 4. It doesn't settle down at a single number, does it? It bounces back and forth. And then another sequence we looked at, those numbers differing by 3, that just blew up to infinity. It never settled down to a finite number. So this issue of whether or not a sequence has a limit is the crucial idea, the crucial concept of dealing with sequences. Let's do another example. I want to now talk a little bit about notation for sequences and then show you kind of a pitfall that comes up sometimes. Let's try to find a rule for the odd numbers. The odd numbers form a sequence, don't they? 1, 3, 5, 7, 9, etc. Those are the odd numbers. What would be a good rule for that sequence? Well, here's one. The rule 2n minus 1 starting with n equals 1. And you would get the odd numbers. As n goes 1, 2, 3, 4, 5, this generates 1, 3, 5, 7, 9. But there are other ways of writing this. You could say, well, the sequence would be 2n plus 1 as long as you start with n equals 0. And that would also generate those same odd numbers. Or you could have 2n minus 3 and start with n equals 2. So there are various forms of the rule that you can have and still get the same sequence. But here's a much more subtle point. Suppose somebody gives you the terms of a sequence, a few terms of the sequence. Suppose they said, here's a sequence, 1, 3, 5. And they ask you the following question. What's the rule for that sequence? 1, 3, 5. Well, you might sort of think to yourself, well, it sounds like it's odd numbers. I'll bet you the rule is 2n minus 1, like we just saw. But you could have a different rule generate those same 3 numbers. Here's a rule that I came up with. Consider the rule minus n cubed plus 6n squared minus 9n plus 5. Kind of an obscure, complicated rule. But if you take that rule and plug in 1, 2, and 3 for n, you will get back 1, 3, 5. It generates the first 3 odd numbers. Unfortunately, when you plug in 4 into that rule, it generates 1. So that rule doesn't work past the 3rd odd number. So the bottom line is, what's the moral of this story? Just given a few terms of a sequence, you might think you know what the rule is. Oh, I think it's odd numbers. But it may not be. It may be a more obscure rule. All right, let me show you now one of the most famous sequences of all time. This is a great sequence. I love it. And it's defined in a somewhat different way. It's called a recursive definition. Let me try to explain it. This sequence starts off with the first 2 terms, and I'll call the first term a sub 0 and the second term a sub 1. The first 2 terms are 1 and 1. So it starts off 1, 1. After that, every term is the sum of the previous 2 terms. So if you start 1, 1, the third term is the sum of the first 2. So the third term is 2. And the next term is the sum of the previous 2 terms, so it's 2 plus 1 or 3. And then it's 2 plus 3, 5. 3 plus 5, 8. And you keep going like that. The nth term is the sum of the nth minus first term and the nth minus second term. Kind of hard to explain that, kind of hard to write that down, but it's the sum of the 2 previous terms. See how that works? And so you get this very famous Fibonacci sequence, 1, 1, 2, 3, 5, 8, 13, 21. It keeps growing. Now, of course, it doesn't have a limit, does it? It's going off to infinity. But here's something kind of interesting. If you take quotients of successive pairs, for instance, 3 over 2, 5 over 3, 8 over 5, 13 over 8, 21 over 13, that sequence of quotients approaches a limit. And that limit is 1 plus square root of 5, all divided by 2. A very famous number that you, well, let me say it this way. I invite you to go to the internet and search for the Fibonacci sequence. It's all over the internet. There are websites devoted to this sequence because it seems to occur all over the place. In nature, a lot of plants have patterns in their leaves and things that are in a form of a Fibonacci sequence. The mathematics of the Fibonacci sequence is very, very deep. We just touched on it here. There's actually a mathematics journal totally devoted to properties of this sequence and related sequences. It's called the Fibonacci Quarterly, and it's a mathematics research journal based on this very famous sequence. By the way, who was Fibonacci? He was born in Pisa, Italy, and traveled widely, and he was one of the early folks to argue that the Hindu-Arabic base 10 number system was superior to Roman numerals. And of course, we know now he was right. We don't use Roman numerals very much anymore. Okay. Sequences. Have we seen some of these earlier in the course? Well, let me remind you, way back in an earlier lecture, we actually saw a sequence. We didn't call it that then, but we saw when we were dealing with compound interest that every year we earned a certain amount of money based on a formula. And that formula, in a specific example, say $1,000 invested at 3% interest, the rule would be 1,000 times 1 plus 0.03 to the nth power. And when n is 0, you have $1,000. That's how much money you put in the bank. After 1 year, you plug in 1 as the exponent and you get $1,030. You've earned $30 of interest. After 2 years under this compound interest, you have $1,060.90. And you go on. That's a sequence of numbers. It's the amount of money you have in your bank account at the end of each year. All right, we're now going to move on a bit to infinite series. This is a beautiful topic in mathematics. You're going to like this, trust me. But we need to set up some notation first. And the first notation I'd like to remind you of, I think you might have seen it already, is so-called factorial notation. And here's what factorial means. You have an integer and you put an exclamation point by it, and that means like 3 factorial or 5 factorial. And what it means is 5 factorial is 5 times 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. 8 factorial is 8 times 7 times 6, down to 1. So the technical definition, n factorial, is the product n times n minus 1 times n minus 2, all the way down 3, 2, 1. So we've done some calculations. What's 2 factorial? That's 2 times 1, or 2. What's 3 factorial? 3 times 2 times 1, 6. What's 4 factorial? Well, I think you get the picture, don't you? 4 times 3 times 2 times 1, 24. And by the way, for notational reasons, mathematicians define 0 factorial, which doesn't make any sense, I know, but just accept it to be equal to 1. And we'll need that in a moment. So 0 factorial is 1, 1 factorial is 1, and then the numbers start growing. Here's some good news. Factorials are available on calculators. There's a key for factorials. Why? Because they're important. And so the engineers had decided to hardwire them into calculators. And factorials can get big pretty fast. I mean, we already saw that 5 factorial, 5 times 4 times 3 times 2 times 1, that's equal to 120. That's pretty big. 20 factorial is a giant number. It has 19 digits. It just strung out. Don't make me read the digits, but it's a big number. Factorials grow quickly. So if you have to calculate things like 20 or 30 factorial, ouch. That's going to be a tough calculation. And here's the second notation I'd like to introduce. It's a notation for summations, how you add up a certain amount of numbers. And it's a very compact notation. Here's how it goes. If you have, say, the numbers a sub 1 plus a sub 2 out to a sub n, so we're adding up n numbers, a compact way of writing that is to use the Greek letter sigma, and you write it as sigma I equals 1 to n of a sub I. That notation means the following. A sub I takes on the values I equals 1, I equals 2, out to I equals n, and you add them up. Sigma sort of sounds like sum. And this index I, by the way, is sort of a dummy variable. It can be any letter you want. It can be K or J or anything. That I has nothing to do with the square root of -1 or vectors or anything like that. It's just a symbol that they use there for the summation. And the lower limit, I equals 1, that can vary. You could start the summation at 0 or at 2, depending on the context of the problem. And the upper limit is n. N might be 5, so you're adding up 5 terms. All right, let's do some examples to make sure we're comfortable with this new notation. Suppose you have the summation from I equals 1 to 4 of 3i. 3i. Well, here's how you should read it. I is going to change. I is going to start at 1 and then go 1, 2, 3, 4. And each time you add up that term. So it's 3 times 1 plus 3 times 2 plus 3 times 3 plus 3 times 4. And then you add those numbers up, 3 plus 6 plus 9 plus 12. That adds up to 30. Now, these summations have properties. One of the most obvious properties is I could factor that 3 outside the summation symbol. Watch what happens when I do that. Now it's 3 times the summation of I. But I goes from 1 to 4 again. So it's 3 times the following sum, 1 plus 2 plus 3 plus 4. And that again is 3 times 10 or 30. So the summation symbol's not too hard. Just sort of keep in mind that it's a compact way of writing a summation. Let me show you a really neat example. And this will, the answer will surprise you. It will trigger some memories. I'm going to add up 1 over n factorial. Remember that notation n factorial we just talked about? And I'm going to start at n equals 0 and go out to 8. So I'm adding up actually 9 terms. Here's what those terms look like. It'd be 1 over 0 factorial plus 1 over 1 factorial, 1 over 2 factorial, all the way out to 1 over 8 factorial. I'm going to add those numbers up. Remember, 0 factorial we define to be equal to 1. So here are the terms of my summation. 1 over 0 factorial is just 1. 1 over 1 factorial, 1 again. What's 2 factorial? 2 times 1 is 2, so that's a half. 3 factorial, 3 times 2 times 1, that's 6, so it's 1/6. And then it's 1/24. And you keep going. 1 over 8 factorial, the final last term of my summation, is 1 over a big number. It's 40,320. That's equal to 8 times 7 times 6, blah, 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 down to 1. All right, I added those up on my calculator. And here's the answer I got. See if you recognize this answer. 2.71828, approximately. 2.71828. Do you recognize that fellow? Have you seen that number before? Wow, that looks like E, doesn't it? That's our friend E. In fact, as you add up more terms, if you were not to stop at 8 factorial, but say stop at a million factorial, you would really be close to E. In fact, here's what mathematicians say. Here's what the theory of infinite series says. If you were to add up an infinite number of these terms, go out to infinity, keep adding, it's exactly E. In fact, that could be a definition of that number E, that strange number that was the base of the natural logarithms. Here it is occurring again in a completely different setting. I mean, one of the things that I love about mathematics is that seemingly unrelated ideas suddenly are glued together. Ideas that appeared in a different context suddenly reappear, as it does here. Okay. I said that there are some surprises with these summations. Let me just mention two more. The summation of 1 over n squared. That would be 1 plus a fourth plus a ninth. It's the reciprocal of the squares. A 4, 9, then it'll be 1 over 16, 1 over 25. That equals, and this you would prove in a calculus class, that equals pi squared over 6. If you add from 1 to infinity, in other words, the sum goes out forever, it adds up to pi squared over 6. Whoa, where did pi come from here? Isn't that neat? Suddenly pi appears. And here's a bonus question for you. What about the sum of the reciprocals of the cubes? 1 plus 1 over 2 cubed, 1 over 3 cubed. That summation, nobody knows the answer. It's an unsolved problem in mathematics. Of course, you could get an approximation. You could take the first million terms and get a decimal approximation. But I want the exact value, like in the previous problem, pi squared over 6 is the exact value. Nobody knows the exact value to that one. Okay, on we go. I'd like to now look at a class of infinite series that are probably the most familiar to us, and I would say the most important in pre-calculus. And this is called the geometric series. Let me show you an example. The summation from n equals 0 to 4 of 1/2 to the ith power. I goes from 0 to 4. That would be the following finite sum: 1 plus a half plus a fourth plus an eighth plus a 16th. And I could add that up, that finite sum. If you get a common denominator of 16, the numerator becomes 16 plus 8 plus 4 plus 2 plus 1. Add those numbers up. It comes out to 31 over 16. Good. Here's the question. What happens if I keep adding more terms? I go out to infinity. I add from I equals 0 to infinity. I don't stop. Does that approach a fixed number? Let's find out. And I'm going to show you some real mathematics now. We're going to do a proof. This is a nice little calculation. I think you'll enjoy it. We're going to try to figure out what the answer is going out to infinity. And the way we'll do it is we'll find the answer out to some number n. And then we'll let n go out really big. So let's calculate the summation from 0 to n of r to the ith power. That's 1 plus r squared out to r to the n. R can be any number. In the previous example, r was a half, and we added up 1 plus a half squared. But r could be a third, or r could be anything. We'll call that sum, 1 plus r out to r to the n, call that x. I want to know what x is. Here's the trick. It's a neat trick. Multiply both sides of that equation by r. So the left side becomes r plus r squared, blah, 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 out to r to the n plus r to the n plus 1. And the right side becomes r times x. And now subtract the two equations, the second equation minus the first. Notice that all the terms on the left cancel. They cancel each other, except for two. Two terms remain, two survive. R to the n plus 1 doesn't have anybody to cancel with. And the 1 in the first equation doesn't have anybody to cancel with. Everybody else has a partner. So the left-hand side simplifies to r to the n plus 1 minus 1. And the right-hand side, of course, is rx minus x. I subtracted. Factor out the x, and we have x times the quantity r minus 1. Divide by r minus 1, and we now have x. x equals r to the n plus 1 minus 1 divided by r minus 1. And it's perhaps better to flip everybody here, write it as 1 minus r to the n plus 1 divided by 1 minus r. That's a formula for the finite sum. Let's check it. I always like to check formulas before I go on. Let r be a half and n 4. That's the problem we just did. If you plug those numbers into this formula, you get 1 minus a half to the 4 plus 1 power, also known as 5, divided by 1 minus r, or 1 minus a half. And the numerator becomes 31 over 32. 1 minus 1 over 32 is 31 over 32. The denominator is a half. Cancel, and you get 31 over 16, which was the previous answer we had. Okay, so now we have our fancy formula for adding up these terms, 1 plus r squared, etc. And it's 1 minus r to the n plus 1 divided by 1 minus r. Now imagine the following. Imagine that r is less than 1 and greater than minus 1. In other words, the absolute value of r is less than 1. That means that r to a large power starts getting smaller and smaller, doesn't it? Like if r were a half, then 1/2 to the billionth power is really small. So in the limit, as we go to infinity, that r to the n plus 1 begins to disappear. And in fact, if you add from I equals 0 to infinity r to the I, that's 1 plus r squared forever. The r to the n plus 1 disappears, and your formula is 1 over 1 minus r. And of course, you have to make sure that the absolute value of r is less than 1. If r is greater than 1 or equal to 1 in absolute value, the series doesn't add up to a finite number. This problem, by the way, arose very early in something called Zeno's paradox. Let me try to explain it real quickly. Suppose I want to travel across this room. I want to cross the room. Let's imagine it's 2 meters long. Well, here's what Zeno says. You'll never get there, because first you go halfway. Then you go halfway again. Then you go halfway again. Then you go halfway again. Well, you never get to the end because you're just adding a half of the previous step. And he argued you never get across the room. And you can sort of see this as an infinite series. We're adding up 1, that was the first step, and then a half, and then a quarter, and then an eighth, etc. But we know better, don't we now that we've studied these infinite series? We're adding this up to infinity. And of course, if you add up to infinity, it's 1 over 2, 1/2 to the I, from I equals 0 to infinity. According to our formula, it's 1 over 1 minus r, which is 1 over 1 minus a half, and that equals 2. So this infinite series out to infinity adds up to 2. Zeno does cross that 2-meter walk. All right, let's play with these infinite series a moment. Here's a problem that often stumps people. Let's talk about decimal expansions for a moment. What does it mean to say the number 0.9999999999999 forever? String of nines forever. Well, let me try to explain what that means. And while I'm doing it, ask yourself, what does 0.999999999 forever really equal? Well, here's one way to imagine what that number is. The 0.9, the first 0.9 really is 9/10, isn't it? And then the second 0.9 is 9 over 100. It's in the hundredth spot. And the third one is 9 over 1,000, 9 over 10 cubed. So we can consider 0.9999999 forever as an infinite series. We're adding up 9/10 plus 9 100ths plus 9 1,000ths, etc. Well, let's add that up with our new fancy formula. And here's how you can do it. Factor out the 9/10, and you're left with 1 plus 1/10 plus 1 over 10 squared, 1 over 10 cubed forever. I recognize that as r being a tenth. R is a tenth. So it's 9/10, that's outside the summation, and then it's summation I equals 0 to infinity of 1/10 to the I. What did our formula tell us to do here? Well, the answer is 1 over 1 minus r, and r here is a tenth. So, first of all, the 9/10 just sits there. It was already factored out. And then it's 1 over 1 minus a tenth. 1 minus a tenth is, of course, 9/10. So we have 9/10 times 1 over 9/10. They cancel, and the answer is 1. Whoa! 0.999999 forever equals 1. Now that surprises a lot of people. It surprises me. The decimal representation of numbers is not unique, is it? The number 1 has another representation as this infinite decimal. I think people, they kind of are hesitant about this. So why don't you be the teacher for a moment? A student comes up and says, I don't believe it. How could you help that student? Well, one way would be the student's comfortable with 0.33333 forever. Multiply that by 3 and you get the same equation we just talked about. Or ask the student the following question. If it's not equal to 1, what is it equal to? And the student won't have a good answer there either. Okay, that was a lot of fun, I think, talking about sequences, especially the Fibonacci sequence. Again, I invite you to go to the internet and explore it some more. And then adding up the terms of a sequence for these infinite series, and in particular the geometric series. There are a lot more series around there. Let me just whet your appetite so you'll study some mathematics on your own. E to the x, our old exponential function, has an infinite series expansion, and here it is, 1 plus x squared over 2 factorial, etc. Okay, so there's a whole world out here with infinite series. But we're going to switch gears. And next lecture and the following, we're going to talk about probability theory. It's a whole new topic, lots of fun because we'll talk about the lottery and rolling dice and things like that. So I'll see you then when we begin counting principles and probability.